Space War. An enemy spaceship is moving toward your starfighter with a speed as measured in your frame of the enemy equals 0.4 c, 0.4 times the speed of light. The enemy ship fires a missile toward you at a speed of v missile prime 0.7 c relative to the enemy ship. So this is measured with respect to the enemy ship. Part A, what is the speed of the missile relative to you? That's v missile. Express your answer in terms of the speed of light. And part B, if you measure that the enemy ship is d is equal to 8 times 10 to 6 kilometers away from you when the missile is fired, how much time measured in your frame will it take the missile to reach you? So I choose S frame as my frame, starfighter frame, and S prime, the enemy, is moving with respect to me with a speed of 0.4 c. So enemy ship is moving in plus I hat direction with v enemy that's measured in my reference frame. And we're looking at a missile that is fired from the enemy ship. The speed of the missile measured by the enemy ship is given. We want to know the speed according to the starfighter in part A. So let's recall the Galilean transformation. We have two reference frames, our starfighter reference frame and enemy ship reference frame that is moving with constant speed with respect to the starfighter reference frame, and they are reporting a position in space, a position P, let's say. The position vector according to the starfighter reference frame is R, according to the enemy reference frame is R prime, and in a time interval t, because the enemy moves with respect to the starfighter by an amount v enemy times t, we have the following relationship between these vectors. R, the position vector according to the S reference frame, R, is equal to R prime, the position vector measured with respect to the enemy reference frame, plus the relative velocity of the S prime reference frame with respect to S reference frame times t. And if this object starts moving, if this point object starts moving, then they would be reporting a velocity, if I take a time derivative, u, velocity reported by the S reference frame, is u prime plus the velocity of the S reference frame with respect to S prime reference frame. And if it accelerates, I take another time derivative, accelerated reported by the two reference frames would be equal. And this is all because the time measured in the two reference frames, t prime and t, are the same. So going with the Galilean transformation, I would see that if it's the missile that's the moving object that we're looking at, the velocity of the missile reported by the starfighter reference frame would be equal to the velocity of the missile reported by the enemy reference frame plus the relative speed, relative velocity of the enemy with respect to the starfighter. Now, what was the speed of the missile according to the enemy reference frame? 0.7 c. So this would be 0.7 c, and the enemy moves towards the starfighter with a relative velocity 0.4 c I hat. So we would find that the velocity of the missile reported by the starfighter reference frame would be 1.1 c I hat. And we know that that contradicts the basic postulates of relativity nothing can move faster than the speed of light. So we have an upper limit on velocities. Therefore, this answer is not correct. Now we have to use the correct transformation between these two reference frames. What is the correct transformation? It's the Lorentz transformation that we should use. Okay, so instead of reporting the x coordinate in this manner, x is equal to x prime plus velocity of the s prime reference frame with respect to s, vn. Now we have this multiplied by t is actually multiplied by t prime, and we have a relativistic correction factor gamma here. Since the motion between these two reference frames is on the x-axis, the position y component and z component reported by these two reference frames are the same because there is no motion on that axis. Now, what is the time transformation? The time reported by the S reference frame is t prime plus x prime v divided by c square multiplied by gamma, the relativistic correction factor. What is gamma? Gamma, the relativistic correction factor, is 1 over square root 1 minus v enemy square divided by c square. So this is the relative velocity of, relative speed of the one reference frame we're looking at with respect to the other. So this is 1 over square root 1 minus the relative speed of the two reference frames square divided by c square. So once again, instead of having x is equal to x prime plus vn times t, we have x is equal to x prime plus vn times t prime multiplied with gamma, the relativistic correction factor, and t prime is not equal to t. T is equal to t prime plus x prime vn, the product of these two, divided by c square multiplied by gamma, the relativistic correction factor. That's our Lorentz transformation of the position and time. Now we have to do a Lorentz velocity transformation. So what happens if I take a time derivative? So if I write these equations in differential form, let's see what happens. So I had x is equal to x prime plus vn times t prime times gamma. Now if this is dx, it's dx prime plus vn, that's a constant, dt prime multiplied with gamma. And the time transformation, dt, it was equal to t prime, it's now dt prime. Now I had x prime times vn, so it's vn times dx prime divided by c square multiplied with gamma. So if I take dx dt, which is the velocity reported by the starfighter reference frame, this will be u, that's equal to so if you take dx dt, we're dividing these two equations. So you will have dx prime dt prime, which is u prime, plus we have v enemy divided by 1 plus v enemy u prime over c square. Okay, so what I do is I take this into dt prime parentheses. So this is actually dt prime times 1 plus v enemy u prime over c square times gamma. Then I divide the top equation with this so that dx prime dt prime is u prime. dt prime divided by dt prime is 1, so I get v enemy. Divided gammas cancel. 1 plus v enemy u prime over c square. What was the Galilean velocity transformation? U is equal to u prime plus v enemy. It is u prime plus v enemy divided by this correction factor 1 plus v enemy u prime over c square. So that's the proper Lorentz transformation. So if I do the Lorentz transformation instead of the Galilean transformation, the velocity of the missile as reported by the starfighter reference frame, the S reference frame, is velocity reported by the enemy reference frame, which was 0.7 c, its speed, and the speed of the enemy with respect to the starfighter was 0.4 c. Now I have 1 plus v enemy times u prime. V enemy was 0.4 c, and then I have u prime 0.7 c divided by c square. So these c's will disappear. So this gives me 1.1 c. The missile is equal to 1.1 c, which is the Galilean answer, divided by 1 plus 0.4 times 0.7, and this gives us our final answer. The velocity of the missile, the speed of the missile with respect to the starfighter reference frame is 0.859 c. Okay. Now let's move on to part B of the problem. Part B says, if you measure that the enemy ship is 8 times 10 to 6 kilometers away from you when the missile is fired, how much time measured in your reference frame will it take the missile to reach you? Okay, so the distance between these two reference frames, as measured in the S reference frame, the starfighter reference frame, was 8.00 times 10 to 6 kilometers. The speed of the missile as measured in the S reference frame, we just calculated 0.859 c. So what's the relationship between the speed and the distance? The time it takes to reach the starfighter multiplied by the speed of the missile is the total distance traveled, d, and these are all in the S reference frame. So I can see that delta t will be equal to divided by d divided by v missile. So this is what it should be. Now if I plug in the numbers, I will see delta t is equal to, so I check the distance, 8 times 10 to 6 kilometers, which is 8 times 10 to 9 meters, divided by 0.859 c, 3 times 10 to 8 meters per second is c. So I find the delta t to be 31 seconds. Okay, So we have an enemy moving towards the starfighter with a relative speed 0.4 c. So this is the speed of the S prime reference frame, which is the enemy, and S reference frame is the starfighter reference frame, and the enemy is moving in plus I hat direction with V enemy as measured in the S reference frame. The enemy ship fires a missile towards us as measured in the S prime reference frame, 0.7 c speed relative to the enemy ship. What is this speed according to the starfighter reference frame? So first I recalled the Galilean transformation. For a position in space, we have, if at time t equals to 0, these two had the same origin, v enemy times t is the position vector of the S prime reference frame with respect to S reference frame, position of the origin. And R, the position reported by the S reference frame, is V enemy times T plus R prime. And T prime is equal to T in the Galilean transformation. They're measuring the same time. Time is absolute in this transformation. So if I take a time derivative, dr dt is u, dr prime dt is u prime, and V and T divided by T is or time derivative is Vn. That's a constant. If this is a constant, if I take another time derivative, that disappears. So the accelerations they will report will be the same. So the velocity of this missile reported by the S reference frame is the velocity reported by the S prime reference frame plus the relative speed of S prime with respect to S, and that gives me 1.1 c in I hat direction, and this is not allowed according to the postulates of theory of special relativity. We have an absolute limit on the speed. Nothing can move with a speed higher than the speed of light. Okay, so Lorentz transformation is the correct transformation to do. So y and z components of the object measured by these two reference frames will be the same because they're moving on the x-axis with respect to each other. And x component is x prime plus vn times t. It becomes t prime, so everything is primed on the right side, unprimed on the left side, multiplied by gamma relativistic correction factor, which is square root of 1 over 1 minus relative speed of the two reference frames squared divided by c squared. And time also is transformed. T is equal to t prime plus x prime b enemy divided by c squared times gamma. So product of these two divided by c squared times gamma. So if I write these equations in differential form, dx is dx prime plus v enemy dt prime gamma, and dt is dt prime plus v enemy dx prime over c squared gamma. If I take the second equation in dt prime parentheses and divide the first equation by the second equation, I obtain Lorentz velocity transformation. U is u prime plus v enemy divided by 1 plus v enemy u prime over c squared. So with the correct transformation, substituting 0.7 c for u prime and 0.4 c for v enemy, I obtain 0.859 c as the speed of the missile measured by the starfighter reference frame. If the starfighter reference frame sees that the missile was fired at a distance 8 times 10 to 6 kilometers, and in the same reference frame the speed is 0.859 c, then the time it takes for it to reach the starfighter will be distance traveled divided by the speed measured, d divided by v missile. So that's going to be 31 seconds.